Welcome back. This is Ms. Rodriguez, and we are on the second part of our human impact screencast. So just as a quick review of the last slide of the prior screencast, air quality has a direct effect on our marine ecosystem, just simply because we have pollution that is being created by fossil fuels, and those fossil fuels, as you learned in the first screencast, are being drilled out of the ocean floor, which leads us to possible oil spills. But on top of that, we're going to see also how the air quality will in turn affect the quality of life in our oceans. Smog is a type of air pollution that's caused by the interaction of sunlight with those pollutants that are being produced by fossil fuels. And a component of smog is particulate matter and ground level ozone. So particulates are microscopic bits of dust, and it can be metal, it can be unburned fuel. They're about 1 to 10 microns in size that are produced by many different industrial processes. So any kind of factories you can think of, they create particulates. Alright, and the chemical formula for it is nitrous oxide plus oxygen will give you nitrogen monoxide and ozone. And that's how we get our ozone. That's a part of smog. Now, acid rain, is a type of precipitation produced when the pollutants in the water cycle cause rain pH to drop below normal levels. So acid rain will reduce the pH in lakes and streams, causing a decline in growth rates. Now, just because the PowerPoint says lakes and streams, it does not say oceans. It very well does affect oceans. Alright, if the air quality got so poor that all of the oceans around the world ended up having their pH levels drop, you would see a decline in growth rates in the oceans as well. And we already have a problem with overfishing, and we already have a problem with hunting animals in our marine ecosystem. Adding acid rain to naturally drop those growth rates would be even worse. So as you can see, like every little thing that's been going on that we've been doing ends up going back into a circle and affecting us anyway. Acid rain is so powerful that it actually can break down the bark on trees, and then those trees would be vulnerable to weather disease. So if it's strong enough to break down bark, it's strong. The drop in pH is strong enough to have a significant effect on just the chemicals that are in our ocean water and the different minerals and elements that are there. Now, the levels of carbon dioxide rise and fall. It's part of a cycle. It's natural that this does this. However, having too much carbon dioxide can be a problem. So carbon dioxide helps keep the temperature of the biosphere in a range that is sustainable to life. And the biosphere is what we consider where all life exists on the planet. So having carbon dioxide helps us maintain a good temperature. We're not too cold and we're not too hot. High levels of the carbon dioxide, though, gives us an overall rise in temperature. Now, if the overall rise in temperature does not stop, we end up with a problem. The problem that you guys know is global warming. However, we are supposed to have higher levels. It's all in a cycle. So Earth's atmosphere has gases called the greenhouse gases that will slow the loss of heat through the atmosphere. And those gases are water vapor, carbon dioxide, and methane being the most common ones. And so you'll see in a couple slides a graphic that shows what we are supposed to have and what we are having. So with all these greenhouse gases, there's an effect. It's called the greenhouse effect. And that's when our carbon dioxide, our water, and our methane absorbs enough energy that is re-radiated by the Earth's surface and slows the release of it back into the atmosphere. So this allows us to have that nice, comfortable temperature. However, when the trend of increasing global temperature continues, then we have what's called global warming. Because now it's no longer a cycle. Now there's no up and down. It's just constantly getting warmer, 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 warmer. There is no drop in the amount of carbon dioxide or drop in the amount of heat that's being released. It just continues to grow. And this is what's threatening ecosystems all around the world. Not just the ocean, but in terrestrial ecosystems as well. With the ocean, however, global warming is raising the temperature of the water, And whether the ocean water only raises 1 degree, it actually makes a drastic effect for everything else. 1 degree sounds like it's not a lot, but for 70% of the Earth's surface to go up by 1 degree, it makes a big difference. Okay, this means that we will have much stronger hurricanes, much stronger typhoons and monsoons. Plain, like, simple example. Look at Hurricane Katrina. Hurricane Katrina went through the Gulf of Mexico, hit a hot spot. That hot spot turned that hurricane from a Category 3 to a Category 5 by the time it landed into Louisiana and caused devastation. Okay, that is one reason why hurricanes occur in the tropics or in tropical areas. The water is warm. It feeds off of the energy of the heat energy that's in the water. You raise the temperature, more chances for hurricanes, more chances for not just like a Category 1 hurricane, but you're increasing your chances, and you're playing with a very, very thin line of whether or not you're going to have some very catastrophic storms coming your way. So, like I said, I referred to this graphic earlier. On the left, this is what we're supposed to have. This is a natural thing. This is when our carbon dioxide was within the normal limits that we're supposed to have. So you see here that you have a thick layer of the atmosphere and a small red layer of greenhouse gases. The sun has solar radiation that comes in, it bounces off the surface of the Earth, and then is re-radiated out into space. But you see there you have a small little arrow. It's a very thin arrow that points back down to the Earth, and that's what helps keep us in that nice, warm, comfortable temperature. When you look at the one on the right, however, you see now that you have very little atmosphere. Okay, there's definitely not as clear. And then you have a very thick layer of red. That very thick layer of red means that we have extreme amounts of greenhouse gases in the atmosphere. Sun's still giving us the same amount of radiation, and there's still the same amount of radiation being deflected off the surface of the Earth. Okay, but the difference is now the thin arrow that we had in the diagram on the left is what's going back out into space. The thick arrow is what's staying, and that's what's making it very, very hot for us. And remember, 1 degree makes a big difference. We're talking about we're melting polar ice caps. Okay, we're raising sea levels, and for those of us who live in Florida, that's a problem. For those people who live on lands or in areas where technically they are below sea level, that's a problem. So again, we're causing this, and it's not only affecting everyone else, it's coming back full circle and still hitting us. And that's what people are failing to realize. So we're going from air quality now into the water quality. And the one way we can see how healthy an ecosystem in the water is by studying the natural indicator species. So an indicator species, also known as a bioindicator, is a species that provides a sign or an indication of the quality of the ecosystem's environmental conditions. So frogs are a good indicator species. We've used dolphins before as an indicator species in certain areas. So we look to see whether they're thriving or whether they're not thriving. If they're not thriving, then we're like, whoa, wait a minute. There's obviously an issue with their ecosystem. What's going on? What's changed that has caused them to react this way? Just as if, the reverse. If they start having, a large growth rate, then it's like, okay, so what positive change has happened in their environment or in their, local area that has caused them to have such a great growth rate? What did we do differently that helped that? So that's what an indicator species will tell us. Okay, we have water-soluble pollutants, and we also have fat-soluble pollutants. Water-soluble pollutants, they'll dissolve in the water. Fat-soluble pollutants, they dissolve in the meat of the fish that we eat. Okay, and this is where biomagnification comes in. With biomagnification, a pollutant moves up the food chain as predators eat prey, accumulating in higher concentrations in the bodies of predators. Biomagnification, best way that you guys may have seen this and not realized it, is when you find out that there are certain kinds of fish that you can have more times than others, and they tell you, oh, you can't have it because there are high levels of mercury in that one, so you got to stay away from that kind of fish. Or you can have this fish, But, you can't eat too much of it, because having too much of it, you'll get mercury poisoning, things like that. That's where biomagnification comes in. And with biomagnification, the pollutants are measured in parts per million. And this diagram here is a good example. We can see that the phytoplankton at the top starts off with 0.025 parts per million of any kind of fat-soluble pollutant. Okay, and then it's eaten by the zooplankton if we follow the arrows just like we would in a food web. So the zooplankton eats it. Well, now it's 0.123 parts per million because zooplankton are eating a large amount of phytoplankton. After that, the small fish are eating a larger amount of zooplankton. Well, now that small fish has 1.04 parts per million. The predatory fish has 4.83 parts per million because it's eating large amounts of small fish. A barracuda does not go swimming in the ocean and say, I think I'm going to have one clownfish for today and I'll be full. It doesn't work that way. Alright? If they're hungry, they are hungry. They eat until they're full. Alright, just look at an example. If you've ever been to SeaWorld, they feed those whales in one show a whole 2 or 3 buckets filled with fish. It's not just one fish, it's a lot of fish. So then all those fish carrying 1.04 parts per million, if you multiply it by however many fish they're taking in, you're multiplying the amount of toxin that's going into them. And then the predatory fish is being eaten by a fish-eating bird, so that's 124 parts per million right there. And then I'm sure there's some hunter that's going to come and shoot that bird and eat it, or we're going to be eating the predatory fish in large amounts, and it keeps going on and on. But the one who's at the top is going to be the one who's affected by the amount of water pollutants in there the most. So biomagnification, like I said, has the greatest effect on the one on the top. And they realized this because they did studies on beluga whales that showed that they had such high levels of toxins that when they washed up on beaches dead, they were considered to be hazardous waste. That means that they had to walk out there with hazmat suits to be able to get rid of these bodies because they were just so toxic. They had so much pollution in them that it was toxic for anyone to be around them without a hazmat suit on. So, yes, this affects our marine food web system, which again throws off the entire marine ecosystem if it continues. But on top of that, humans are also affected by it because we eat that. So again, we're causing the issue. Full circles back to affecting us as well. Now we have our threats to biodiversity. Humans are the main threat. We have a major impact on biodiversity. We are threatening animal and plant populations. Okay, and the thing is that many of our medical and technological advancements have come from nature. Loss of biodiversity can make an ecosystem unstable. If an ecosystem is unstable, it can collapse. One ecosystem collapses, and it goes ahead and dominoes all the way through the rest of our ecosystems. And once something is extinct, it's gone forever. Yes, do we have the technology to do stuff like Jurassic Park? We do. But it's never going to be the original species. Never. It's not going to happen. Okay? Just even looking at the example of Jurassic Park. To get the T-Rex, they had to put different reptilian DNA to complete the DNA sequence in order for them to create something that looked like a T-Rex. Okay, once something is gone, it's gone forever. We're not going to get it back. Megalodon is gone. It's extinct. It's not coming back. The best way to protect the species is through conservation. Okay, and we have the World Wildlife Fund that does conservation. We have OCEARCH, which is a big one for marine science. They tag and track sharks all over the world, so that way you can actually see in live time, real time, where these sharks are going. And it's mainly to see, where are they mating? Where are they having their babies? What are their migration patterns? Are they in an area with high traffic human interaction? And are we doing something to them that's causing this issue? Okay, and then, of course, development has caused habitat loss. Habitat fragmentation is when a barrier forms that prevents an organism from accessing its entire home range. Coastal development is habitat fragmentation for some of the organisms that live out on the beach. Alright, so this is going to conclude the second screencast as far as the ocean and human impact on the ocean. We've got one more coming up that'll sum up the rest of the lesson. And that'll be the end of this chapter.